The Incredible Universe. Extraterrestrial Life Part 1. Extraterrestrial life, colloquially referred to as alien life, is life that may occur outside of Earth and which did not originate on Earth. No extraterrestrial life has yet been conclusively detected, although efforts are underway. Such life might range from simple forms like prokaryotes to intelligent beings, possibly bringing forth civilizations that might be far more advanced than humankind. The Drake equation speculates about the existence of sapient life elsewhere in the universe. The science of extraterrestrial life is known as astrobiology. Speculation about the possibility of inhabited worlds outside the planet Earth dates back to antiquity. Multiple early Christian writers discuss the idea of a plurality of worlds, as proposed by earlier thinkers such as Democritus. Augustine references Epicurus's idea of innumerable worlds throughout the boundless immensity of space, originally expressed in his letter to Herodotus, in The City of God. In his first-century poem De Rerum Natura, Book 2 to 1048–1076, the Epicurean philosopher Lucretius predicted that we would find innumerable exoplanets with life forms similar to, and different from, the ones on Earth, and even other races of man. Pre-modern writers typically assumed that extraterrestrial worlds would be inhabited by living beings. William Barillon, in the 15th century, acknowledged the possibility that Christ could have visited extraterrestrial worlds to redeem their inhabitants. Nicholas of Cusa wrote in 1440 that the Earth was a brilliant star, like other celestial objects visible in space, which would appear similar to the Sun from an exterior perspective due to a layer of fiery brightness in the outer layer of the atmosphere. He theorized that all extraterrestrial bodies could be inhabited by men, plants, and animals, including the Sun. Descartes wrote that there was no means to prove that the stars were not inhabited by intelligent creatures, but their existence was a matter of speculation. The writings of these thinkers show that interest in extraterrestrial life existed throughout history, but it is only recently that humans have had any means of investigating it. Since the mid-20th century, active research has taken place to look for signs of extraterrestrial life, encompassing searches for current and historic extraterrestrial life, and a narrower search for extraterrestrial intelligent life. Depending on the category of search, methods range from the analysis of telescope and specimen data to radios used to detect and send communication signals. The concept of extraterrestrial life, and particularly extraterrestrial intelligence, has had a major cultural impact, especially extraterrestrials in fiction. Over the years, science fiction has communicated scientific ideas, imagined a wide range of possibilities, and influenced public interest in and perspectives on extraterrestrial life. One shared space is the debate over the wisdom of attempting communication with extraterrestrial intelligence. Some encourage aggressive methods to try to contact intelligent extraterrestrial life. Others, citing the tendency of technologically advanced human societies to enslave or wipe out less advanced societies, argue that it may be dangerous to actively call attention to Earth. Astronomers have discovered stars in the Milky Way galaxy that are almost 13.6 billion years old. Extraterrestrial life, such as microorganisms, has been hypothesized to exist in the solar system and throughout the universe. This hypothesis relies on the vast size and consistent physical laws of the observable universe. According to this argument, made by scientists such as Carl Sagan and Stephen Hawking, it would be improbable for life not to exist somewhere other than Earth. This argument is embodied in the Copernican principle, which states that Earth does not occupy a unique position in the universe, and the mediocrity principle, which states that there is nothing special about life on Earth. The chemistry of life may have begun shortly after the Big Bang, 13.8 billion years ago, during a habitable epoch when the universe was only 10–17 million years old. Life may have emerged independently at many places throughout the universe, as it arose on Earth roughly 4.2 billion years ago through chemical processes. Alternatively, life may have formed less frequently, then spread, by meteoroids, for example, between habitable planets in a process called panspermia. In any case, complex organic molecules may have formed in the protoplanetary disk of dust grains surrounding the Sun before the formation of Earth. According to these studies, this process may occur outside Earth on several planets and moons of the Solar System and on planets of other stars. Since the 1950s, astronomers have proposed that habitable zones around stars are the most likely places for life to exist. Numerous discoveries of such zones since 2007 have generated numerical estimates of many billions of planets with Earth-like compositions. As of 2013, only a few planets have been discovered in these zones. Nonetheless, on the 4th of November 2013, astronomers reported, based on Kepler space mission data, that there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of Sun-like stars and red dwarfs in the Milky Way, 11 billion of which may be orbiting Sun-like stars. The nearest such planet may be 12 light-years away, according to the scientists. Astrobiologists have also considered a follow-the-energy view of potential habitats. Life on Earth is quite ubiquitous and has adapted over time to almost all the available environments in it, even the most hostile ones. As a result, it is inferred that life in other celestial bodies may be equally adaptive. However, the origin of life is unrelated to its ease of adaptation, and may have stricter requirements. A planet or moon may not have any life on it, even if it was habitable. A study published in 2017 suggests that due to how complexity evolved in species on Earth, the level of predictability for alien evolution elsewhere would make them look similar to life on our planet. One of the study authors, Sam Levin, notes, like humans, we predict that they are made up of a hierarchy of entities, which all cooperate to produce an alien. At each level of the organism there will be mechanisms in place to eliminate conflict, maintain cooperation, and keep the organism functioning. We can even offer some examples of what these mechanisms will be. There is also research in assessing the capacity of life for developing intelligence. It has been suggested that this capacity arises with the number of potential niches a planet contains, and that the complexity of life itself is reflected in the information density of planetary environments, which in turn can be computed from its niches. The first basic requirement for life is an environment with non-equilibrium thermodynamics, which means that the thermodynamic equilibrium must be broken by a source of energy. The traditional sources of energy in the cosmos are the stars, such as for life on Earth, which depends on the energy of the Sun. However, there are other alternative energy sources, such as volcanoes, plate tectonics, and hydrothermal vents. There are ecosystems on Earth in deep areas of the ocean that do not receive sunlight, and take energy from black smokers instead. Magnetic fields and radioactivity have also been proposed as sources of energy, although they would be less efficient ones. Life on Earth requires water in a liquid state as a solvent in which biochemical reactions take place. It is highly unlikely that an abiogenesis process can start within a gaseous or solid medium. The atom speeds, either too fast or too slow, make it difficult for specific ones to meet and start chemical reactions. A liquid medium also allows the transport of nutrients and substances required for metabolism. Sufficient quantities of carbon and other elements, along with water, might enable the formation of living organisms on terrestrial planets with a chemical makeup and temperature range similar to that of Earth. Life based on ammonia rather than water has been suggested as an alternative, though this solvent appears less suitable than water. It is also conceivable that there are forms of life whose solvent is a liquid hydrocarbon, such as methane, ethane or propane. Another unknown aspect of potential extraterrestrial life would be the chemical elements that would compose it. Life on Earth is largely composed of carbon, but there could be other hypothetical types of biochemistry. A potential replacement for carbon should be able to create complex molecules, store information required for evolution, and be freely available in the medium. To create DNA, RNA, or a close analog, such an element should be able to bind its atoms with many others, creating complex and stable molecules. It should be able to create at least 3 covalent bonds, 2 for making long strings and at least a third to add new links and allow for diverse information. Only 9 elements meet this requirement: boron, nitrogen, phosphorus, arsenic, antimony, 3 bonds, carbon, silicon, germanium and tin, 4 bonds. As for abundance, carbon, nitrogen, and silicon are the most abundant ones in the universe, far more than the others. On Earth's crust, the most abundant of those elements is silicon. In the hydrosphere it's carbon, and in the atmosphere, it's carbon and nitrogen. Silicon, however, has disadvantages over carbon. The molecules formed with silicon atoms are less stable, and more vulnerable to acids, oxygen, and light. An ecosystem of silicon-based life forms would require very low temperatures, high atmospheric pressure, an atmosphere devoid of oxygen, and a solvent other than water. The low temperatures required would add an extra problem: the difficulty to kickstart a process of abiogenesis to create life in the first place. Even if extraterrestrial life is based on carbon and uses water as a solvent, like Earth life, it may still have a radically different biochemistry. Life on Earth started with the RNA world and later evolved to its current form, where some of the RNA tasks were transferred to the DNA and proteins. Extraterrestrial life may still be stuck on the RNA world, or evolve into other configurations. It is unclear if our biochemistry is the most efficient one that could be generated, or which elements would follow a similar pattern. However, it is likely that, even if cells had a different composition to those from Earth, they would still have a cell membrane. Life on Earth jumped from prokaryotes to eukaryotes and from unicellular organisms to multicellular organisms through evolution. So far no alternative process to achieve such a result has been conceived, even if hypothetical. Evolution requires life to be divided into individual organisms, and no alternative organization has been satisfactorily proposed either. At the basic level, Membranes define the limit of a cell, between it and its environment, while remaining partially open to exchange energy and resources with it. The evolution from simple cells to eukaryotes, and from them to multicellular life forms, is not guaranteed. The Cambrian explosion took place thousands of millions of years after the origin of life, and its causes are not fully known yet. On the other hand, the jump to multicellularity took place several times, which suggests that it could be a case of convergent evolution, and so likely to take place on other planets as well. Paleontologist Simon Conway Morris considers that convergent evolution would lead to kingdoms similar to our plants and animals, and that many features are likely to develop in alien animals as well, such as bilateral symmetry, limbs, digestive systems and heads with sensory organs. The planetary context would also have an influence. A planet with higher gravity would have smaller animals, and other types of stars can lead to non-green photosynthesizes. The amount of energy available would also affect biodiversity, as an ecosystem sustained by black smokers or hydrothermal vents would have less energy available than those sustained by a star's light and heat, and so its lifeforms would not grow beyond a certain complexity. Planetary habitability in the Solar System. Some bodies in the Solar System have the potential for an environment in which extraterrestrial life can exist, particularly those with possible subsurface oceans. Should life be discovered elsewhere in the Solar System, astrobiologists suggest that it will more likely be in the form of extremophile microorganisms. According to NASA's 2015 astrobiology strategy, life on other worlds is most likely to include microbes, and any complex living system elsewhere is likely to have arisen from and be founded upon microbial life. Important insights on the limits of microbial life can be gleaned from studies of microbes on modern Earth, as well as their ubiquity and ancestral characteristics. Researchers found a stunning array of subterranean organisms, mostly microbial, deep underground, and estimate that approximately 70% of the total number of Earth's bacteria and archaea organisms live within the Earth's crust. Rick Colwell, a member of the Deep Carbon Observatory team from Oregon State University, told the BBC, "I think it's probably reasonable to assume that the subsurface of other planets and their moons are habitable, especially since we've seen here on Earth that organisms can function far away from sunlight using the energy provided directly from the rocks deep underground." Mars may have niche subsurface environments where microbial life exists. A subsurface marine environment on Jupiter's moon Europa might be the most likely habitat in the Solar System, outside Earth, for extremophile microorganisms. The panspermia hypothesis proposes that life elsewhere in the Solar System may have a common origin. If extraterrestrial life were found on another body in the Solar System, it could have originated from Earth just as life on Earth could have been seeded from elsewhere. Directed panspermia concerns the deliberate transport of microorganisms in space, sent to Earth to start life here, or sent from Earth to seed new stellar systems with life. The Nobel Prize winner Francis Crick, along with Leslie Orgel, proposed that seeds of life may have been purposely spread by an advanced extraterrestrial civilization, but considering an early RNA world, Crick noted later that life may have originated on Earth. Thanks for watching. Please like and subscribe.